Hello, welcome to another college math video. In this video, we'll keep working on geometry, but now we're going to get into those three-dimensional shapes and look at a few more aspects of them. So our objectives, only two, find the surface, surface area. Hello. Hopefully it's updated on your printed notes. Surface area and volume of three-dimensional figures, and then the volume of shaded regions. So we saw similar types of feeling problems in the last video, and this video is going to have a lot of the same feel. We just get more complicated looking shapes. So two things we're looking at, surface area and volume. Surface area, in most general terms, it's a square measurement, and you can always imagine that you're covering an object with wrapping paper. So the surface area formulas they look pretty complex. You'll always have to have all of that information, but it's because there are so many objects that we're coding. So we talked about area being covering a two-dimensional flat thing with sticky notes. We're doing the same thing with surface area. It just has to happen to the front, to the left, to the right, to the back, to the top, to the bottom. And that's only on this type of shape. We'll have all types of shapes that we're coding with wrapping paper. But that's the general idea. What's the lowest amount of wrapping paper you could use to coat that object? And so since, again, we're talking about covering with paper, this is going to be a square measurement. So units squared, feet squared, inches squared, whatever the unit might be with a exponent of 2 next to it. Again, not a computation. Doesn't mean that there's anything additional that you're doing. It's a unit of measure. It means how many squares does it take to coat the object. Feet squared, inches squared, whatever it might be. And then volume is a cubic unit of measurement because this is where we're taking that object and then filling it with sand. Sand is a good visual image. Even better, I think, is imagining cubes of Jell-O because this box doesn't want to open now. There we go. So you can imagine, sure, you could fill this object with sand, but you can also imagine the number that we're going to come up with, 54, is how many cubes of Jell-O. You could cut little cubes of Jell-O to be all the same size and then stack them. And sometimes we'll get decimals for the same reason that sometimes we have to chop them, sometimes they have to get shaved to fit certain shapes, but that's when we're filling an object. So that's our three-dimensional one, is volume. So again, cubic unit of measure, units, cubed, feet, cubed, inches, cubed, and that's because it takes cubes of Jell-O, cubes of something to fill the object. So in the end, when you're deciding what your unit should look like, come back to, would I use Jell-O to fill this? Would I use paper to cover it? Or would I use string to go on the outside of it? In this video, it'll be all about either paper or potentially Jell-O. Okay, so the formulas. For a rectangular solid, we have the volume formula, length times width times height. Brace yourself for the drawing of these shapes. This one's just a box. So if you draw a rectangle and then shoot lines off of 3 of the sides in the same direction, same length, and then just make those corner pieces, you'll see it. The 3 things you would need to know: length and width. You can really label them any way that you want. Length are the 2 on the bottom, width would be the other 2 on the bottom, and then height is the one making it a three-dimensional object coming up from the bottom. But again, if you labeled this one H and this one L and this one W, it's not going to make a difference. Surface area, again, like I said, these formulas are going to be a bit more complex because it's complex to cover each side of these shapes. So this box actually is a rectangular solid, so I can point this one out. We have 2 times, if this is, let's make sure it matches. Okay, if this is sitting similar to how you're seeing it, oh my gosh, close, there we go. You've got length times width. Length times width, that's the bottom, times 2 because there's a top and a bottom. Width times height, width times height. This is kind of this side, width times height. But there's a left and a right, so times 2. And then length times height, this one times this one, the front and the back. There are 2 of them, so times 2. So that's where the formula comes from. It's literally just finding the area of each surface and then adding them together. This just condenses it. you'll be told if it's a rectangular solid, or it'll be clear from the picture that it's a rectangular solid. All right, the next shape we have is a cube. This very specifically means that all the sides are the same. So cubes of Jell-O, that's why the unit is cube, because it's a perfect cube then. The formula for volume is very simple. A side length cubed, because each side length is the same. My picture obviously doesn't show that they look the same, but imagine that they were exactly the same size. And then surface area, if we were looking for the area of one of the sides, the 6 wouldn't be here, we would have s squared. But there are 6 sides, so whatever that number is, multiply it by 6. Front, back, top, bottom, left, right. 6 sides of a cube. You can picture a single die that you would roll. It has 6 different sides, which is why on a standard die there's 1 through 6. It would be length times width, essentially, to get one side, which is just side length squared, and then times 6, since there's 6 of them. All right, cylinder. Volume formula. Let's get the picture in there first. Draw kind of an oval, the same matching oval top and bottom. Connect the 2 sides. There's only 2 things that you need to know. From the middle of the circle, this could be in the top or the bottom, to the outside, just the circle portion. You can picture a can of soup. If you were looking at it from the top down, you would see a perfect circle. We're looking at it from the side, so that's why we're not exactly seeing a perfect circle. You would need to know radius of the circle anywhere down the line, and then you would also need to know the height. So looking at it from the front, top to bottom, what is it? If you have those 2 things, you can fill in the formula. The volume is pi r squared h. Remember, pi r squared is the area of a circle. So imagine that's the top. And then times h, now we're filling the object. That's where we get the 3rd dimension from. And then surface area is broken into 2 pieces. Imagine you were trying to coat a can of soup with paper, with wrapping paper. We have 2 pi r h. So 2 pi r was our formula for the distance around. It's sort of like if you pulled the label on a can of soup off, 2 pi r is the distance on the bottom, and then times h is the height of that. So that gives you the outside of the can of soup. And then pi r squared is the area of the top, times 2 because there's a top and the bottom. That's just where the formula comes from. I'm not going to ask you to describe to me in detail how these formulas exist. This is just to give you an idea. And again, you would not be expected to have these formulas memorized. You'll be given them, but you need to know, okay, what shape does that look like, and then be able to use the formulas. All right, a couple more. We have a cone. Go with another oval, 1 point at the bottom, and have them come down. You can sort of picture this as a little paper cone sometimes that you get water with. To fill this up volume-wise, pi r squared h. Pi r squared h was our cylinder formula. So imagine if all of this was a cylinder. It's 1/3 because we're missing, it just so happens to work out nicely like that, that it's 1/3 of it. That's your formula for volume. And then surface area, again, is quite complex. Pi r squared is this circle at the top that you're coating with paper. Then you also have to create the paper that is the bottom of the cone, or if you're picturing an ice cream cone, that would be, this second part is just that. Covering at the top would be the first part. Pi r square root of r squared plus a squared. No easy way to explain that one because that one's a bit complex, but that's what it would look like in the formula. The 2 things that you would need are the radius from the top circle all the way out, and then the height. And the only way that that can be indicated is from inside that center portion all the way down to the bottom. And just so you can see the 3rd dimension, I'm going to add in an additional ring to kind of make it pop. So this line is going directly down the middle. You can picture what an ice cream cone looks like. All right, and then our last shape is a sphere. So this is any sort of ball. I'll draw the globe, basketball, baseball, anything like that. Again, this should be perfect. I know that my drawing is not quite there. The formula for volume, 4/3 pi r cubed. No easy way to explain that. The only thing you need to know is the radius. Again, pi, just look out for whatever an online system asks for. 3.14, we're typing in pi, or leaving pi in as the answer. And then surface area, 4 pi r squared. So again, no really easy way to explain where that comes from, but that's your formula for if you were taking that ball and coating it with paper. Very difficult to do if you've ever tried to wrap anything like that. But it is possible, and that's how much it would take. Keep in mind, if we're doing the units for all of these, anytime it's volume, so for a sphere in particular, we're filling it with cubes of Jell-O. So you would use units cubed, and then surface area is coating paper on the outside, so it would be units squared. Okay, so let's see these formulas in action. Oh, a couple more notes. Volume of a couple more, prism and pyramid. A prism in particular means that the shape has the same top and bottom. And the formula is very basic looking. Capital BH, where capital B means area of the base. I'll draw a couple examples. Let's take that out. Yeah. So a prism has the same top and bottom, so maybe it has the same triangle top and bottom, and then it's connected. It could be a trapezoid. Nope, let's make that a little nicer. Prism just means same top and bottom. So very simply, to find the volume, how much it would take to fill that object, find the area of one of the bases, top or bottom, and then multiply by h to fill the object. So whatever shape you have on the bottom is what you would need to focus on, and multiply by the height. And the volume of a pyramid has the same type of feel. This formula is volume equals 1/3 base times height, where again, B means capital B. Means area of the base. But there's only one base here. That could be any shape. Again, I'll draw a couple examples. Let's say it was a triangle, all going up to one particular spot. I'll shade to show this is the base. Then filling up, so you need to find the area of that triangle, multiply by the height, multiply by 1/3. That would give you the volume of that shape. Surface area is possible for these, coating the object. There's no easy way to come up with a general formula. It would just be literally finding the area of each surface. How many different surfaces are there? We could have a square base going up to a top. Again, this being your base. You could have a 6-sided figure, anything. Anything that you're able to find the area of the base, and maybe you'd already be told that in this situation, times the height times 1/3. We've seen lots of area types of questions, so adding these in isn't anything new. You could find area of lots of different shapes of these bases, and then the rest of the formula times height times 1/3, or just times the height, depending on if it's a prism or a pyramid. Okay. All right, so let's see some examples. The first one, we're looking for volume and surface area of the figure. First, we have to identify what shape we have. This one, very simply, is a rectangular box. Some people often will say cube, but the only way it's a cube is if all of the measurements are exactly the same. So rectangular solid is what we have here. Let's start with volume. Is length times width times height. So do we have all three of those things? Length, width, and height? We do. You could label them however you want to. I'm going to go ahead and call this one the length, this one the width, and this one the height. If you started out labeling them in any other way, that's fine. You just have to pick one and stick with it. All right. So we have all three of those. Length is 4. Width is 3, and height is 2. Multiply those three together. We get 24. We have a unit here, it's meters, and the question is volume. So is this regular meters, square meters, or cube cubic meters. This is volume, this is filling the object, so these are cubic meters. Okay, there's volume. Surface area, the formula is, I'll write it below, a little bit longer. 2 times, now I'll list it the same order that I had it in there, but it doesn't really matter. 2 times length times width, 2 times width times height, 2 length, height. And just plug in, you know length, width, and height, so it's just a matter of plugging them in. 2 times 4 times 3, 2 times 3 times 2, 2 times 4 times 2. Multiply 2 times 4 times 3. 24. 2 times 3 times 2, 12. 2 times 4 times 2, 16. Add them together, we get 52. We are given a unit of meters, and since this is surface area, we are coating this object with paper. All of the different ones. Total, it comes out to meters squared. Coating with paper means meters squared. So there are your 2 answers. This is if we have the exact shape that the formula calls for. It won't exactly always happen like that. Okay, so let's do this one. Find the volume of the shaded area. Now, the picture does not have shading filled in, so I'm going to go ahead and fill it in. We've got this cube, the whole cube there, and then imagine that this cone is cut out. So I like to picture, I guess you could picture Jell-O, but I usually say cement. Imagine it's a cement cube, and then from underneath, the cone has been shaved out. So what exists is around the outside of the cone. Now it's in the front all the way around, but we just have a shaved out cone in the middle. So how do you think we approach this? The same way we approached one of the problems in the last video, get the volume of the entire thing as if the whole figure existed, which in this case is a cube. I would have to tell you that it's a cube since it doesn't necessarily say that. And then subtract out the volume of what's missing, which is the cone. So we want volume of cube minus volume of cone. So let's get each of those formulas. Volume of a cube is side length cubed. Volume of a cone, 1/3 pi r squared h. Okay, so let's start with cube. We want a side length. We have that listed here. It's 10 centimeters, so 10 to the 3rd power. You can type that in the calculator. You get 1,000. We'll hold on to that number for now. Then for our cone, we need the radius and the height. Radius is halfway across. So 10, if we know the whole thing, because it's going all the way across, is the diameter, which means the radius is 5. Whoops, not 1/2, 1/3. Pi 5 squared. And then the height, how do we know what the height is? Well, it's a cube, so every measurement, length, width, height, is 10. So the height is 10. Multiply what we can. Order of operations says the exponent first. 1/3 pi 25 times 10. Then we can do 25 times 10 is 250. You could get a decimal with the 1/3. I'm just going to pull them together like this for right now. Because again, we run into if we wanted an exact answer, this would be the value we have. If we were looking for an approximation, type it in the calculator, 1,000 minus 250 over 3 pi, pi coming after it, 1,000 minus 250 over 3 pi, 738.1 decimals, good, 0.2. And then don't forget the units. These are centimeters, but it's a volume measurement, so it's cubic. We're talking about how many cubes of Jell-O it would take to create the cement block. And same thing here, centimeters cubed. Just depends what the system is looking for. If it wants an exact, you type this in. If it wants an approximation, look out for how it says to use pi and then give them the decimal. All right, so that's the second example. So again, big picture, we looked for volume of the entire shape as if it all existed, and then subtracted out the cone that was missing. Okay, so let's do some practice problems. I've got two. The first one is like the first problem we did, find the volume and surface area of the figure. The second one, we're looking for volume of the figure, and I have to draw it in. Yeah, let's go here. No. This can be done. The values, this is 9, this is 8, 4, and 10. Okay, so with all that information, you should be able to find the volume of this figure. Every connecting line forms a right angle. So that makes it so you can figure it out. Pause the video, we'll see if we're on the same page in a minute. Okay, first problem. Volume and surface area of the cylinder. This is very straightforward, just using those formulas. Volume formula is pi r squared h. So we have the height listed for us here, 11.5. The radius we don't exactly have, but we have the distance all the way across, which makes the radius half of that, 3.5. Pi 3.5 squared h. Whoops, not h. We know h. 11.5. So I'll do 3.5 squared times 11.5. We have pi times 140.875. This would be your exact answer. Almost centimeters. This is volume cube. And then your approximation, that number times pi, 442 point, rounds up to 6 centimeters cubed. Okay, so there's our volume. Surface area, yeah, I think it'll fit down here. The formula, 2 pi r h plus 2 pi r squared. We have r and h, so just plug them in. 3.5 times 11.5. So I'll do 2 times 3.5 times 11.5. This is 80.5 pi. And then 3.5 squared times 2. 24.5 pi. Those are like terms, so we actually could add them together. 80.5. We get 105 pi. This would be your exact. Since this is surface area, we're coding with paper. This would be centimeters squared. Or your approximation, 105 pi. 329.9 centimeters squared. Just depends, approximation or exact, whatever it's looking for. Okay, so that was pretty much just plugging in numbers using those formulas. The second question, a little bit more complex. We don't have a formula for that shape, but we can kind of modify and use one of our formulas. So you can sort of picture No, I don't want the whole thing to go away. You can sort of picture, so I don't want to draw on here, as if the rest of this existed. So this looks like one step, but you could picture that this could get filled in. This missing chunk of stair could get filled in, and then we would have a rectangular solid. There's a couple different ways to approach this. You could approach it the exact same way that we approached the second example problem, which was imagine that the whole shape existed, a whole rectangular solid with this height of 10, and then subtract out the missing piece. Or you could cut this into two shapes, two different rectangular solids, So cut right here and have front and back, or cut right here and have top and bottom, and then add them together. Either way would give you the right answer. On the other problem, we didn't really have a choice. Here we do have a choice. So let's just use the subtraction method. It's the one that I would think of, but whichever way worked for you is totally fine. I promise you the answer will be the same either way. So we want volume of the whole rectangular solid, subtract out the volume of the missing rectangular solid. So the formula is pretty straightforward: length, width, and height. Let's do it for the large shape first, as if this entire thing existed. Well, we see 9 times 8 and 10. Those are all three of the numbers we would need. So as if the whole rectangular solid existed, it would be 720. And then the missing rectangular solid, what's missing is this piece right here, the 4 by 4 by 10. So we actually have all of them. 4 by 4 by 10, 160, subtract, we have 560. We don't have anything listed, so we'll just say units. And we are looking for volume, so these are cubic units. This is one way. If you had cut the figure into two, let's say you did top and bottom, I won't go through the entire thing, you would get 560. If you did top and bottom, let's say you cut here and you've got this top piece and the bottom piece. You need length times width times height. Okay, so we have 8. We don't have this measurement. How do we get this measurement? Well, we know that the whole thing is 9 and a missing chunk is 4. 9 minus 4 means that this piece is 5. So 8 times 5 times 10 plus the other piece. How do we know what this piece would be? We have this one. Again, the whole thing is 8. Part is 4, which means the other part is 4. 4 times 10. So add those two numbers together, you would get 560. And a similar thing happens if you were to cut the other way. But that's kind of what these problems will potentially look like. So this video was all about surface area and volume of three-dimensional objects. Surface area always feels the most complex to students. The formulas are complicated, but it's because there are so many different places that we're coding with paper, and then volume is then filling those objects. Remember that those units are going to be important when it comes to anything that's written and that you would turn into me. Online homework systems typically will put those there for you. All right, so I'll see you soon for another video.